So, good evening, everybody, or good morning in Japan. My name is Holger Dette. I'm professor of mathematical statistics at Ruhr University in Germany. You might not know where this is. It's close to Cologne, 80 kilometers north of Cologne. So I will be talking about statistical inference for comparing small population groups. And this is based on joint work with many people. It's actually Katrin Möllenhof, who works as a PhD student in the project, Kirsten Schorning. He's a postdoc in my group, Stanislav Volgev, a former postdoc in my group, and Frank Gritz from Novartis, who actually initiated these questions. The talk will be a little mathematical. I hope you are not scared, but the advantage of mathematics is that you don't have to change anything after you have put something. So I guess we will improve current methodology quite a bit, and I hope I will convince you that we have here a very good methodology. So this is, I don't know how to go down. No? This is what we are going to do today. I will talk briefly about the similarity of curves, and then I will present the current state of the literature for testing the similarity of curves. I will then convince you that good designs will improve this current methodology quite substantially. And after that, I will improve the test itself. So we have two improvements of the current methodology. One is by design of experiments, and the other one is by just defining some new tests, which are much better. Okay, and then we talk a little bit about further results and extensions. I can try to boost the microphone a little bit. I just saw it. This is now better. If you hear me a little better. The problem is that a little bit. Okay, I can also speak louder if you like. Okay, so this is difficult, I guess. I don't know why it's so difficult. Let me see. So usually this works quite well, but I don't know. So I try to speak a little louder, and Diane is, many people type. So sorry, this is confusing. This chat is confusing me a little bit. So sorry. Okay, so now I speak a little louder, and maybe the people on the floor will hear me, or it doesn't matter. Anyway, so let me repeat the outline. So I will talk a little bit about the similarity of curves. Then I will present you the current state of the art, the test for the similarity of curves, which is conservative. And then I will present some experimental designs which will actually improve the power of this test quite substantially. And after that, I will try to improve the test itself. So I will present a better test, and after that, we will conclude with some further results and extensions. So I don't know how to screen here. So this is a typical example. We have two dose response curves from different populations, for example, European and Japanese. So, and the question is if these curves are similar, such that you can use data from one population for the other. So we want to extrapolate data from one population to the other, provided that the dose response curves are similar. Okay. So if you formulate that mathematically, you have two dose response curves. So this is common terminology. So we have observations y, I, j, k. I corresponds to the group. So we have two groups. And in each group, we have those levels, xij. So we have in each group li those levels. And then we have a regression function, mi, and we have a parameter, theta I, in each model. And then we have some kind of errors. For simplicity, we assume that they are normally distributed, but that's not the main point. So those response curves in the usual way we write them. And the question is now, again, are these curves similar? And if they are, then we would like to transform information from one population to the other. Okay. So this means now if we want to talk about similarity, we have somehow to define, oh, this was too fast, sorry. We somehow have to define a measure of similarity. And what we do here is somehow to compare the curves by their maximal deviation. So we take, maybe a picture is easier, so let's go to the next slide. So this is the maximal deviation. So I just have an example. We have an Emax model, which is the curve model. Then I have a log linear model, okay? And then we draw these two curves. And you see this little red line. This is the maximal deviation between the two curves. Okay, and we can now go back. If we now go back, we define the maximum deviation just by taking the difference of the two curves at the point x, takes the absolute value and takes the maximum difference. Okay, and similarity is defined by specifying a threshold, which I call delta. This is a little triangle. If you don't know Greek, this is a little triangle, delta. And so we now consider the curves as similar if the maximal deviation between the two curves is smaller than delta. So the maximal deviation is denoted by d infinity. Okay, so what we want to test is that the maximal deviation between the curves is larger or equal than delta against the alternative that it is smaller than delta. Okay. So I don't get any feedback. So here's again. So I didn't specify in this example delta, but we have these two curves, and we have the red line, the length of the red line is the maximum deviation between the two curves. Okay, and if this maximum deviation is small, then we would consider the curves as similar, and small is just defined by this pre-specified constant delta. So this setup is very similar to bioequivalence testing. So if you are aware of bioequivalence, and the people do something very similar. Okay, so here's the state of the art, what people are doing right now. So we have this hypothesis of similarity. So the maximum deviation between the two curves is, we want to test if this is larger or equal than delta against the alternative that it is smaller than delta. And what the people do is they construct a uniform confidence band. Don't be so confused by the uniform confidence band. Just remember confidence band. They construct a confidence band for the difference of the two curves. And then they reject the null hypothesis if the rectangle, those space, Cartesian product between the interval minus delta delta contains this confidence. So this sounds very complicated, but with the picture it's quite clear. I have a picture here. You see, this is no, I don't have any pointer, so it's difficult, but this black line, we have two black lines. This defines a confidence band for the difference of the two curves. Okay, it's constructed from data. Okay, and then you construct a rectangle which is located, which is somehow marked by the dotted red lines. Okay, you have these two dotted red lines, And now what we see is that this confidence band is not contained in this rectangle. Okay? This means that we cannot reject the null hypothesis that the maximum deviation between the two curves is larger or equal than 2.25, which is a pre-specified concept. And the important point here now is, if you want to increase the power of your test, you need a smaller confidence band, because we reject the null hypothesis only if the confidence band is contained in the rectangle. Okay, so the power is increased if we somehow make the confidence band more narrow. Okay. All right. So now what we want to do here now is I have to explain you a little bit how this confidence band looks like. So this is not. I cannot avoid this. I'm sorry about that. But if you don't understand how this confidence band looks, you cannot improve it. Yeah? And I want to improve it because the procedure which I currently present should not be used, because I don't think it's good. Okay, so what we have here, we have two samples. We have dose levels, x11 up to x1L1 in the first sample, and at each dose level we have observations. For example, in the first sample at dose level x11 we have n11 observations. The same as we have for the second sample, we have dose levels x21 up to x2L2, and at x21, for example, we have n21 observations. Okay, and this is called a design in the literature. So, and this is denoted by the Greek letter psi1 for the first sample and psi2 for the second sample. Okay, so this is just an abbreviation. Okay, but if we have these two samples and we have observations drawn according to these samples, then we can do maximum likelihood estimation for each model. So in each model we can estimate the parameter of the model. For example, in my previous example, we have this Emacs model. We have three parameters for the first sample, so we estimate these three parameters, and the same for the log linear model. Okay, so then we have these two parameter estimates, theta1 hat and theta2 hat, and then we can estimate the difference for the two curves by just plugging in the parameters in the Emacs model, for example, and the log linear model, and then we form just the difference. Okay. All right. So now to get the confidence band, we need. Why is that's not readable? I don't know. Now it's better. So now we get a confidence band. So we take this estimate for the difference, and then we just take, like an elementary class, plus minus standard deviation. This is plus minus standard deviation multiplied with some quantile. So this is just the same as in a baby statistics class. But here now the standard deviation is complicated. So I don't give you the formula. This is this number gamma hat. So this is the standard deviation at the point x, and the standard deviation at the point x depends on the two designs. Okay, and then you see a D. A D is a quantile, which is determined by bootstrap. Okay, and then you have the 1 over the square root of the total sample size. Okay, the important thing what you have now to note here is that the widths, we want to have narrow bands, we want to have narrow confidence bands, that the width of the band at the point x is proportional to this expression gamma of x psi 1 psi 2. So it depends on the design. Okay, so the design, so we can try to choose the designs to get this width of the confidence band smaller. That's what we're doing next. Yeah? But before that, I want to mention these two improvements. So what I want to do now, I want to somehow choose a design such that we get small confidence bands. So this is the first part of my talk. This will be very brief, but you can look at our Annals of Statistics paper to see how this work is done rigorously. And then after that, I still want to improve. I still want to propose a better test for this purpose. So I don't think that this confidence band approach is very good. Actually, I will demonstrate that it has not very much power. Okay, so let's go back to the design question. So I go back here in the first line. We have the confidence band. It's estimate plus quantile divided by square root of the sample size multiplied with standard deviation. And the standard deviation depends on the two designs, and it's a point where we estimate the difference. So it's gamma x psi 1 psi 2. Okay, so we have these two designs, and now what we want to do is we want to somehow determine them in optimal way, and for that purpose we have to, I will assume that the proportions for both samples are fixed, so we somehow fix the number of patients treated with treated in group 1 and the number of patients treated in group 2, but we can choose the allocations of the dose levels to the patients, and we can also choose the number of different dose levels, and we can choose the dose levels themselves. And I want to determine that all these things in an optimal way, and I've already indicated how I do this. This is my next transparency. So I remember that the width of the confidence band is proportional to this quantity gamma, depends on the point x where we evaluate the confidence band, and it depends on the two designs, and I don't give you the formula. But an optimal pair of the designs will now minimize the maximum width of the confidence band. So it takes the maximum of all these gamma expressions and minimizes with respect to the choice of the design. I don't tell you how, and I don't tell you how we get the solutions, but what you should keep in mind is we choose the two designs in such a way that we try to minimize the maximum width of the confidence band by the choice of the design. Okay? All right. And here, I didn't tell you details, but what I do now in my next transparency, I determine locally optimal designs, and which somehow assumes that some preliminary knowledge about the unknown parameters is available. Yeah? Yeah? So I will answer this question in the chat a little later. Yeah, so let me just continue. Yeah? Okay, let me just finish the design part, and then I will answer some questions in the chat. Okay, so we assume that some knowledge regarding the unknown preliminary parameters is available. Yeah, but you can go away from that, but things getting more complicated, and I don't want to go into that, but some people know about this, so if we can do adaptive designs or Bayesian designs, whatever you want, all these things can be done in this context, but I want to keep these things simple. So what I have here now is just a solution for my simple example. I have these two models, and what you now see, I just give you the solution for group 1. The optimal, so for group 1, we should, so the pair of optimal designs is the following. For group 1, we should, roughly speaking, treat 1/3 of the patients at 3 dose levels. One is 0, one is 0.22, and the other one is 1. And for group 2, we should also treat 1/3 of the patients at dose level 0, and dose level 0.15, and at dose level 1. And this might not be so convincing, but what I show you now is the confidence band that we get for the difference of the curves. Okay, what you see now here is confidence bands obtained from two designs. On the left part of the figure, you see the confidence bands for the difference of the two curves. If you would use a standard design, the standard design is basically equidistant in a logarithmic scale. So this is the confidence band if you use the standard design, and on the right-hand side you see that you get it, as you see the confidence band which you would get if you would use the optimal pair of designs. And you see it's much narrower, so which means that the test of Gesteiger et al. Would have much more power. And that's also confirmed in a small simulation study. So here we have a sample size 20 for two populations. We run a simulation study, simulate the power of the test for the two curves. Okay, I think delta is, yeah, now I think it's okay. So delta is still 0.225. And what you see now here is the column for the optimal design. You see that the test has substantially more power than compared to the test of the which uses the standard design. Okay, all right, good. So this is the first part of my talk, I guess, and now I can try to answer the question that you have here. There was one question. So the question was, if we believe a log linear dose response model is appropriate for the second population, why would we attempt to test if it's similar to the Emacs dose response model in population European? So the reason why we want to do this is, at least I'm not a biostatistician, but that's what my colleagues from Novartis were telling me, is that if you, for example, are interested in the minimum tolerated dose level, then these two dose levels, minimum tolerated dose levels, might be similar, even if the curves are different. So if the curves are very close, even if they are different curves, an Emacs and a log linear model, if they are very close, the minimum tolerated dose levels might also be close. On the other hand, you could also use an Emacs model for the first population, or for both populations. Okay, so this is a matter of taste, but what I'm saying is it's not necessary that the two models are close, but as long as they are close, are the same, sorry, but as long as they are close in the maximum deviation distance, then we can extrapolate the minimum tolerated dose from one data to the other. So that's something like this. I hope this answers a little bit. Okay. Another question, let me see. Oh no, that was the only question. Okay, we now go on, and what I wanted to convince you in the first part of the talk is that you should use design of experiment to improve the performance of your procedure. So I gave you one procedure. The procedure was already published 5 years ago, and I just improved the procedure substantially by using an appropriate design. So the example, the standard procedure has no power at all if you don't use an appropriate design, and we should always keep that in mind. So my next part is, so if it's, when Frank Breetz was showing me this procedure, I was immediately saying this is not a good one. This procedure cannot be optimal, and I want now to demonstrate you that this procedure is not a good one. So I want to construct a better procedure, a more natural procedure than this confidence band procedure. I know that in the biostatistics community, many tests are constructed that way, and it's my impression that many of these tests are not good. So, and I demonstrate this here now for the testing for similarity. Okay. So what I want to suggest instead of this confidence approach is the following. So what I want to do is so basically we want to test the hypothesis in the middle so that the distance between the two curves is larger or equal than the pre-specified constant delta against the alternative that it is smaller than delta. Okay, what we propose here in Bochum is to estimate this distance directly. Okay, and then so we estimate this distance directly. That's a red box. I will explain you a little bit later how we get this estimate. It's quite simple. And then we just reject the null hypothesis if this estimate is smaller than a pre-specified critical value, Q. And the only problem that you have here is to find this value, Q. And this is a very challenging problem from a mathematical point of view, but practitioners don't have to bother about that because we solve this problem for you. So we give you this critical value later on, and I will explain a little bit how we give it to you. And there's actually an R package where you get this. So the main idea is don't go with confidence bands, just estimate the distance which you are interested in direct. And I should now explain you how we do that. It's actually very Simple. So our distance is the maximal deviation between the two curves, and so we have these two curves. These two curves depend on unknown parameters, theta1 and theta2. We just estimate these two parameters. Okay, then we have, and then we form the, then we get the distance of the estimated curves. It takes the maximum deviation of the estimated curves, and that's our estimate for the distance. So estimation is very, very simple. Okay, the question now is how to get the critical values. I have here, so usually what people do is very often to use asymptotic theory to get the critical values. This works also in this case. So if the sample sizes are larger or equal than 25, you can somehow get critical values by an approximation of the distribution. I wrote this here as 1 over standard deviation times some complicated distribution. Yeah, so which I denote by Z, and Z is the maximum of a stochastic process. So even if we would have large sample sizes, the critical values are not available because this is really a complicated expression. We can work it out and we need it later, at least when we construct an alternative procedure. But in our project, we are not interested in large sample sizes. We are especially interested in small populations, and that's the reason why we cannot use this result anyway. Okay, so what we propose instead is to do some kind of bootstrap approach. So what we're trying to do is to generate data under the null hypothesis and then try to obtain the quantiles by bootstrap. And the difficulty here is, compared to classical hypothesis testing, is, I go back now, is that the null hypothesis is rather large. So the null hypothesis consists of all parametric curves which have a distance larger or equal than delta. So this is difficult, and this makes the bootstrap approach more complicated than usual. Okay. Okay, and what we do here is, so we try to generate data under the null hypothesis under the worst case. So what we do is we estimate the parameters from the original samples. Okay, and we do this under the restriction that the distance, oh, there's a typo here, that the distance between the two curves is precisely delta, which is my pre-specified constant. Okay. So what we do is we generate constraint estimates under the null hypothesis. That we actually exactly at the boundary of the null hypothesis, that the distance between the two curves is precisely delta. Here on the transparency on the slide, there's an epsilon here. I'm not sure if you can see my mouse here, but this should be a delta. Okay. All right, and this should be also a delta. Okay, and if we have these estimates, this is actually not so easy, but it's doable. Then we generate bootstrap data with a parametric bootstrap. We estimate the variance, we generated normally distributed responses, and then we just generate bootstrap data as a null. All right, and when we have done this, then we from this simulated data, we just get an estimate, a bootstrap estimate of the maximum deviation between the two curves. Okay, and then we generate a bootstrap sample, and we take the bootstrap quantile, and we reject the null hypothesis whenever our original statistics is smaller than the bootstrap. So if this is too complicated, then you just have to remember, as takeaway message, that we have a procedure to get the quantile of the test by bootstrap. And the bootstrap is not a standard bootstrap. So this makes it also interesting for me as a mathematician. It's not a standard bootstrap. It has not been used before, I think. Okay, and there are some theoretical properties. So what we can prove is, that this is really providing an asymptotic level alpha test. We will see what asymptotic here means. It's about sample size is 10. And we also can prove that it is consistent. And what I also want to keep in mind is something which is very typical for these interval hypotheses. The probability of rejection is precisely alpha if you are at the boundary of the null hypothesis. So if the distance between the two curves is practically delta, then the probability of rejection is close to alpha. It is smaller than alpha if you are somehow very far in the interior of the null hypothesis. So if the distance between the two curves is very large, substantially larger than the threshold, the probability of rejection is smaller than 0. And if the distance between the two curves is smaller than the threshold, then you are the alternative, then we can actually show that the probability to reject is close to 1. Close to 1 depends on the sample size. That's what we should know. Okay, I have here my example. Another example, we have an Emacs model and an exponential model. We could have here, because of the other question, we could have here two Emacs model, the curves, and we want somehow to test if these curves are similar, and we shift the exponential model up and down. You see here two red curves, and these two curves correspond to different intercepts. So if delta is smaller, for example, 0.75, the curves would be considered as not so similar, but if you shift delta more upwards, delta is 1, we would consider the curves as more similar. They are never precisely the same. We only want to see if the maximum difference between the curves is not too large. Okay, here's the simulation setup. These are a lot of equations. You don't have to look at them so difficult here. Maybe important is the parameters for the Emacs model are 1 to 1, and the parameters for the exponential model are delta, which actually specifies how far we are from specifies actually the difference between the two curves, and 2.2 and 8. Okay, and we are interested in testing the hypothesis that the two curves differ between that the difference maximum deviation between the two curves is larger or equal than 1 against the alternatives that it is smaller than 1. Okay, and what you see now here is actually the approximation of the nominal level. Okay, sample sizes are very small, and maybe you recall my last point. My last point was that that the level should be close to the nominal level, so to alpha, if we are at the boundary of the hypothesis. So it's the difference between the two curves is 1. So then the level should be close to 1, and we see at least for the 10% level, the level of the new test is very close to the nominated level. Okay. We also see that the test of Steiger et al. Does not keep its nominal at all. So it's very, very conservative. Okay? And what you see now here also is if you move in the interior of the null hypothesis, so if the true difference between the curves is substantially smaller than the pre-specified level, which is 1 in our case, then the level of the test is substantially smaller than alpha. This is actually desirable because we want to have a small type 1 error and a small type 1 and type 2 error. Okay, and here you see the power. Okay, also for very small sample sizes. What you maybe, and I actually added the sample size is 50, which in both populations, which actually does not correspond to a small population trial, but I just want to demonstrate that the test of the Steiger has also some power if the sample sizes are sufficiently large, but it definitely has no power if the sample sizes are small, which you see here in the right part of the table. Okay, and what you see in our in the middle columns, you see that our test has power, and yeah, power is not to 1, but if you have small samples, you cannot expect this. You have to live with some kind of small power. Okay. Yeah. So what else did we do? So if you want to try this, there's a nice package implemented by Katrin Möllenhoff. It's called testing similarity. And we also have extended these things. So, for example, we can compare several curves, like analysis of variance. And we can also treat models with common parameters. This common parameters means that some of the parameters are the same. For example, if we have two Emacs models for the two populations, it might be reasonable to assume that the intercept is the same because the intercept somehow correspond to a placebo effect, which might be the same for female and male persons. Okay, and what we also did is some kind of robustness investigation. And this was also already one question to check if their assumptions are, if the tests are robust with respect to model specific. All those response models have a very similar structure, and actually, what we investigated is if we changed, for example, an Emacs model to a log linear model, if the test is if the results are really changing, but this is not the case. The results are rather robust if you just use the usual models which are used in those response studies. Okay, let me draw some conclusions here. And what I really want to emphasize is that the test of Steiger has no power in the case of small sizes or large variances. So it's not really good if you want to establish similarity of the curves, because that's actually the goal what we want to do. Okay. What I want to emphasize, this was the first part of my talk, that we can, or you can, if you ask us, improve the power of the test of Steiger et al. By the use of optimal design. This was the first part of the talk. And more important is that there exists a substantially better test, which we have developed in the last year. It's interesting. So for you, the message just there's a nice R package where you can use this test. For us as mathematicians, the interesting thing was that we could do non-standard mathematics, which has never been done before. And the difference between the Steiger test and our approach is that the Steiger test somehow works with confidence intervals, but our test is based on an estimate of the distance between the two curves. Okay, and the other point is that we use a standard non-standard bootstrap approach to generate quantiles. And what we now do in the remaining part of the EDR project is to improve the power of the new test by optimal design. So we can now do the second step as a first step again for the new test, and we can do that. So we can improve the power using optimal designs of the new test. And the other point is what we're currently doing with the European Medical Agency is that we use our results to compare dissolution profiles. Okay, and if you look at dissolution profiles, then the data is correlated. So you have dependency between different observations. But here in my talk, I just talked about independent observations. Each observations correspond to a different patient. But with dissolution profiles, this is not the case. So what we did is we extended our approach to models with correlated observations, in particular dissolution profiles, which are somehow different. And I'll give you just that's my last transparency, I guess. I'll just give you a typical dissolution profile here. And these are the typical profiles. And you see now here we have one patient who is measured after 10 minutes, 20 minutes, 30 minutes, and 50 minutes, I guess. And then you have all these dependencies. The message is that everything can be extended. And we're currently writing a paper with people from the EMA comparing our approach with the standard methodology for comparing curves for comparing curves in the context of dissolution profile. And I think I don't have any. No, I have one more transparency here. Yeah, so you see some kind of references and I think the important part for you might be might be the last one. This is just the R package where we provide the necessary software for our approach. And that's all I have to say. And I would like to thank you for staying so long, and I hope it was not too much mathematics, but I'm quite convinced that this is the solution of the problem. Thanks a lot. So I have a question on slide 14. I may not be able to answer this, but I hope Katrin is still online. Let me see, page 40. Okay, so what was your question? Oh, no, this is easy. I can answer this. No, that's easy. No, the designs are not optimal with respect to D or V optimality. The point is, I go back now to transparency 12. So the design, so we have a pair of, so if you look at the last line, there we have this strange standard deviation for the estimate for the difference of the two curves, which I denoted by gamma, and I didn't give you a formula. Okay, so I didn't give you a formula. The formula has is very long, so I don't give you the formula. And what we do now here is at each x we have this standard deviation. We square it. We take the worst case and minimize this standard deviation with respect to the choices of the two designs. This is an optimality criterion which has never been considered before in the literature. So I have no idea how I would call it, to be honest. So it's not D or V. It's a new optimality criterion, and the properties of this new optimality criterion are investigated in this annals paper. So it's a, I would say it's an optimal. The annals paper is optimal. It's an optimality criterion for comparing curves. Let's say it that way. Okay, there's another question. Your examples always had the same number of doses for the two curves, but the formulation is very general. This is true. I'm not sure. You have to type now what you mean. In the constraints, I don't think that in the constraints I added any dose levels or number of doses, something like that. I don't think that the number of doses are added in the constraints. The only constraint that I have is, where's the constraint? It's a constraint in the parametric bootstrap, which is here. So it's on page 21. You see, so where we estimate the parameters theta 1 under the hypothesis that the distance between the two curves is equal to, that was, sorry now again for the typo here, that is equal to my pre-specified constant delta. That's the only constraint, and I hope you understand, so there's nothing in there, okay? The next question is if you want to take the observations in both populations at the same dose levels. No, this is not an advantage. Then you actually lose power. So you should really calculate the optimal designs, and usually the dose levels for both samples are different. Okay. So no more questions? Okay, if there are no more questions, then I would like to thank you once again for your audience, and I hope that whenever you will compare curves, that you will think about our methodology, and of course you can also send me an email if you have further questions later on. Thanks a lot for your attention.